Buzz, John Black, superchemist. We're here to talk about electronegativity today. Uh, I'll go over a couple vocabulary words. Basically, the only one that really matters is the word electronegativity. And that basically just tells you how much an atom wants an electron, wants or needs an electron. Remember how I said that you want an octet? They all want eight electrons in their valence. So if an atom like chlorine has 7, it's going to want an electron really bad because that's all it needs to, be a full octet, right? Like carbon has 4. It doesn't know whether it wants to give them away or take them. It's not very needy one way or the other. What about like say sodium or potassium? Now they only have 1 electron in their valence orbit, so they're going to want to give away. I mean, it's going to be impossible for them to get 7 more electrons, right? But to give 1 away, that might be easy, right? So it's not really wanting electrons, it's wanting to give them away, right? So it would not be considered electronegative. But the chlorine and the fluorine and them up there, they all have 7. All they need is 1 more. That's all they need to be noble, be perfect. So they really want it. They don't just want it, they need it. They have to have it. And that's all electronegativity is how much that atom wants the electron. If it wants it a lot, then it's really electronegative. If it doesn't want it that bad, it's not that electronegative, right? And if it's, like I said, if it only has, like the carbon, it's not really electronegative or electropositive. It's kind of in the middle, but the ones that are in the first row, potassium, the more they get over to the left by sodium, they're more electropositive. Because they're on the opposite side of the periodical table. Anyways, these next two, I'm just bringing up this next one because a lot of people confuse it with electronegativity. And it really is a different thing because it's the amount of energy that's released when an electron is added to a neutral atom or molecule to make a negative ion. So it's basically just the energy. When you add an electron to something, it releases energy. And this next one, ionization energy, that's just the opposite. The amount of energy not released, but that you have to put into the system when an electron is not added, but taken away. Think of it this way. If I get a rock and I glue it to a wall, and there's no energy for me to do that. I just put the rock up to the wall with some glue, right? And that glue gets hot when it's working. It releases heat. It's just like this. You put an electron on the wall and glue it, it's going to release heat. It's going to release energy. It's going to release, you know what I mean? It's no effort to glue a rock to a wall. But now what if I want to take that rock off? This is super magic glue, right? So now I need a crowbar to get that rock off. I'm prying it off. I can't get it off. I got to put energy into it. I got to, work for it. It's just like if you take an electron off, you're going to have to work for it. You're going to have to give some energy, right? But if you put it on, it's no big deal to just glue it on, or you just set it on there and pap, it's there. That's how I always think of it, to remember which is which, because they're basically just the opposite. So let's go back to electronegativity. Look at this bottom part here. That's the periodical table, okay, or close to it. You can see I got the groups 1, 2, 3, 4, all the way up to 8, or the noble elements. They call them noble elements because that's what everyone strives to be. It's like noble metals are gold and platinum, silver. That's what we all want. We strive to be. We strive to have. What are the atoms? They strive to be noble. They strive to have 8 electrons in their valence electron. So look at how these arrows are pointed, where they're pointed at, up and to the right. So this element compared to these elements over here, these ones are more electronegative. Just like on the top. And why is that? Remember, these are marked. These are the groups. They're marked by their valence electrons. If you have 1 valence electron, we already said, you're not going to want to try to get 7 more. You're going to want to try to get rid of that one so you have an empty valence orbital and a full valence orbital. You know what I mean? You emptied out your 1, now you're down to the next lower 1. You have 7 and you're in this group over here. The more you get over here, the more electrons you have. if I have 7, it's easier to get one than to give 7 away. I'm talking about electronegativity when you're talking about the groups going from 1 to 8 or 1 to 7 or whatever. It's a good analogy saying they want it. Whoever wants it more is more electronegative. But if you notice, going up and down affects electronegativity. The higher you are, the more electronegative you are. And if you think about it, the higher you are on the periodical chart, the smaller you are, right? So look at these two atoms here. The positives being nucleus with the protons and the neutrons, right? And the circle representing, even though they're not really circles, representing the electron, okay? Now, if you have a big giant atom, the valence electrons are going to be so far away that the power to attract, you got your positive inner nucleus and your electrons are negative. To get that electron to come in there is tough, you know what I mean? They're just dangling on here. But when you have a small atom, say like chlorine instead of bromine, this would be chlorine, a smaller atom, that positive charge is very close to the electron can come right in there and it's going to be snagged up real easy. It's going to want that. It's going to have more power to get it. This one doesn't have the power as much as this does. So this will be more electronegative. Not as much because it wants it more, but because it has the power to get it. You know what I mean? So it is more electronegative. It will attract the electron easier than, say, this guy, because you'll never get in close enough to get a real good attachment to that electron as you will with this smaller atom. Now, there's this guy named, I think his name is Linus Pauling. He came up with this scale. You can see this is basically the periodic chart. I didn't do any of the D blocks. They're taken out, you know what I mean? These are just the regular ones. You got your periods, your left and right columns, and you got your groups, your up and down columns. And he assigned each one of these elements a number, 2.1, 1. See how they go down? As you go up, you get higher. You get more electronegative, so you have a higher number. Just like I said, if you go to the right, it gets higher. 1, 1.5, 2, 2.5, 3, it keeps, and if you go diagonal, 0.8, 1.2, 2, 2.1, 3, it's always going higher if you're going up or to the right. Basically what he said was this, and this isn't like a hard, mathematical thing, but you can do this real quick and it gives you the, close, estimate. So if you have two, we're going with binary stuff here. So if you have two atoms forming a salt, right? You take the two Pauling numbers and you take the difference of them. So let's say you got fluorine and lithium, since they're nice even numbers, right? 4 minus 1, what's the difference between 4 and 1? 3. So it has a Pauling number of 3, right? Chlorine has 3 and sodium has 0.9. So that's a difference of 2.1. It has a Pauling number of 2.1, right? Or electronegativity number of 2.1. So what does that tell you? Well, there's several kinds of bonds. Covalent, ionic, polar covalent. Basically, he's saying if the difference between those two numbers is greater than 2, you can be considered ionic, an ionic bond. If it's lower than 2, you could be considered a covalent bond, okay? It's just basically a way to think, is this covalent or is this, ionic? You could do this easy math, look up the numbers, do the math, and there you know. Like if you have a carbon, 2 carbons, right? What's the difference between 2.5 and 2.5? It's 0. That's definitely lower than 2. So that's a covalent bond. All right, so what is a covalent bond? A covalent bond is just a bond between atoms where they're sharing the electrons evenly. or somewhat evenly. Uh, Ionic bond is where they're sharing the electrons unevenly, where it's unfair. Okay, and technically, unless you're sharing your electrons exactly even, you know what I mean? You're a covalent bond only if you share them exactly. I mean, technically. But like we said with the Pauling scale, you know, anything above 2 is ionic, and anything below 2 doesn't have to be 0. It could be 1.5 and still be considered covalent. But technically, if you're not 0, if your Pauling's number is higher than 0, the difference between your two numbers, atoms, you are polar covalent. Technically, I guess. So everything is basically polar covalent, except for the ones like that have exact electronegativity numbers. That way, their Pauling's number will be 0. The difference between those. So like hydrogen, oxygen, any carbon-carbon bonds, silicon-silicon bonds, those are all covalent. They have to share evenly. They have the same exact electronegativity number on the Pauling scale, right? But what about sodium chloride? You see, chlorine has 7 valence electrons, where sodium only had 1. But the chlorine took it because that's the only way that he'll have an empty valence orbital. Chlorine will have a full one, and that's what they want. They either got all or nothing. They got, you know what I'm saying, to be good. So this he's more electronegative because you can look on the Pauling scale and see that he has a bigger electronegativity number. So that means he's hogging the electrons more. He wants them more. He needs them more. He has to have them. He has to do it to be noble. Otherwise, he's nothing. And the sodium accepts it because it will have an empty valence orbital, which means it has a full one in the previous orbit. So it's happy too. Same with calcium oxide. The oxygen is more electronegative. It's the one that takes the electrons. And keep in mind that the calcium still shares these electrons. They're still sharing, you know what I'm saying? It's not like the calcium has no access to these electrons. It's just to remember where the electron resides, okay? The orbital is just an area of space where it's at, right? Changes more for the oxygen. There's more chance of it to be around the oxygen, near the oxygen, but it still is around the calcium also. But it's just the percentage, the probability of it being there is a lot less. Okay? You might say, well, what's this all leading to? Who cares who has the electrons? Who cares who's more electronegative? Well, basically, that's because chemistry is based solely on this principle. You need to know what electronegativity means and how to use it. Here's a drawing of a picture of acetone. Okay? I drew it up bigger here so you can see the carbon and the oxygen. Which one's more electronegative? The oxygen, according to the Pauling scale, right? So, if this is more electronegative, that means it's going to hog the electron more. There's going to be more times where the electron is over here than it is over here by the carbon. That will make this side of this whole molecule up by the oxygen, it'll put a negative charge on it. You know, partial negative charge. Down here, since it's not going to see the electron as much, you're putting a partial positive charge down there. What does that all mean? That means that now you have a carbon here with a positive, partial charge on it. A nucleophile or a negative entity can come in. A negative, any kind of electrons, lone pair electrons or some kind of negativity to it can come in and attack here and attach itself to that molecule. That's what chemistry is based on. And you can't know that without knowing electronegativity, because that's what all reactions are based on. So anyways, you guys all have a great day, and always remember, science is great.